So in this section, I'm going to look at a really interesting problem that arises in a microservice architecture, namely the problem of maintaining data consistency. So to understand the problem, first thing we want to look at is the database architecture in a microservice application. There's actually a couple of different approaches that you could use. One is a shared database, so multiple microservices sharing the same database, or you could have a database per service. There are various issues that you need to address when deciding which of these approaches to use. So some business transactions might need to update data that's owned by multiple services. If you think about transferring money between bank accounts, that could involve a money transfer business object as well as a couple of account objects, and those could very well be owned by different services. Likewise, the example that I've used earlier, where when you place an order, you have to check that the customer's credit has not been exceeded. That's actually a transaction that's owned by, that's a transaction that's updating data that's owned by multiple services, the order service and the customer service. Also, some queries might join data that's owned by multiple services. You might want to show a customer and their most recent orders, so that's kind of doing a join between customers and orders. Another issue you want to think about is different services have different data storage requirements. So some services might have data that fits the relational model. Other services might be doing text search. So that's sort of a whole different kind of database. Other services might be searching a social graph. Perhaps that needs a graph database, and so on. Databases also might need to be replicated and sharded for scalability and availability. And then there's a really important thing that we need to address. Services must be loosely coupled so they can be developed and deployed, scaled independently of one another. Let's look at the shared database pattern. So this is sort of a traditional, in a way, legacy approach, right? So we actually have multiple services, order service, customer service, and we have the database. And the order service, well, that has owns the order table, but it also needs the customer table because it wants to verify that the customer has enough credit. Likewise, customer service primarily updates the customer table, but maybe if it wants to compute the available balance for a customer, then it queries the order table. So that's one strategy, sharing a database, accessing each other's data. And on the one hand, that's quite straightforward. You have, it's easier operationally. There's just one database, only one sort of moving part, so to speak, that you have to set up and manage and so on. Also, it means that everything is a local transaction. You can use regular ACID transactions that we're very familiar with. But there are some big downsides. The fact that these services are accessing one another's data means that they're really tightly coupled. The team working on the order service can't really change the order database without actually having to go talk to the team that's managing the customer service, because it's accessing it too, and there could be all kinds of other services accessing the order table. And in some companies, they might not even be sure who's accessing which database. It can get messy and out of control, and you can end up being afraid to actually change a table because you don't know the consequences of doing that. And then there's a very practical issue. A single database might not satisfy the data access needs of all of the different services. As I mentioned, some services might need a text database, other services might need a graph database, and then other services might be fine with a relational database. It all depends. But this notion of having the database is often not a good fit. So the other option is to have a database per service. So the order service has its order database that contains the order table. Customer service has a customer database that contains the customer table. And if the order service needs to access data about the customer, it actually has to talk to the customer service and vice versa. Now there's several different ways of achieving this. You could actually have a single database server. It just means that a service owns its tables within that database and no one else can access them. That's just a rule, and maybe you can enforce it using a security mechanism of the database. Or similarly, a service could have its own database schema that's private to it. No one else can access it. Or in some cases, a service could have its own database server. It depends. There's different ways of realizing this. But one nice thing about this architecture is that it escapes the constraints of using a relational database for everything. As I'm sure as you're familiar with, relational databases tend to have issues around scalability. They tend to have issues around scaling across multiple data centers. Sometimes updating a schema can be a problem with a relational database. You might actually have to touch every row in a table to add a column. And if the table is very large, that can take a very, very long time, hours in fact. And then there's always this problem that applications can have like this rich object model, and then you actually have to map it to this flat relational schema. And there's a real mismatch between those two worlds. Also, the relational model tends not to be good at handling semi-structured data. Tables have a fixed number of columns, and if you have business entities with a varying number of attributes, that doesn't map nicely to a database table. So what this means that you can do is actually take a step back and for every service ask questions like, what is the velocity and the volume of the data that service is processing? What kinds of data is it processing? Is it binary blobs? Is it relational, or is it text? Is it graph? Does the application need to support ad hoc queries, or is there a fixed set of queries baked into the application? What's the latency? How long does it need to take between an update being made to the data and that update showing up in queries? If you think about big data and Hadoop, that's very high latency, but that's good enough for some situations. How distributed does the data need to be? Does it need to be in multiple data centers and being updated in multiple data centers simultaneously? And also, what are the access patterns? Is it very read intensive, or is there a mix of reads and writes, or is it very write intensive like a logging application? So you can ask those questions, and then for each service, pick the kind of database that best suits that service. Could be SQL, could be key value, could be text search, or it could just be blob storage, something like AWS S3. So it all depends on the needs of a particular service. So you end up now with an architecture where we've got microservices. So that's good, we understand that. But now we also have multiple databases, and they can be of different types. So for sake of an example, customer database could be a sharded SQL database, whereas the order database could be a NoSQL database like MongoDB. So we have this polyglot persistence architecture as well as a microservice architecture. So there are benefits, right, to doing this. So services are loosely coupled. Each service can use the database that's appropriate to its needs. But then there are some really interesting downsides. As I mentioned at the beginning, you might need to implement transactions and queries that span multiple services. Doing that in this architecture is challenging because now you're spanning multiple databases. and it's more complex to operate. You could actually have a mix of different kinds of database servers, and there's more of them than just the database. So operationally, it's complex. But yeah, a big issue, especially for the application developer, is we now have these distributed data management problems. So like when it's time, when we're placing an order, right? If the order database is a NoSQL database, we don't have ACID transactions, so we could typically only update one thing atomically within that database. And we very likely do not have two-phase commit between multiple databases. That's sort of problematic technology to use. Yet at the same time, we need to maintain invariants. So the example that I introduced earlier was the notion that customers have a credit limit, which means that when you place a new order, you have to verify that doesn't exceed the credit limit for that customer. If there's just one database, you can accomplish this using ACID transactions, though there's some wrinkles around isolation levels. But if you've now partitioned the system and there's now two different databases involved, there's a real issue with maintaining these invariants. So we sort of got this kind of tension, right? On the one hand, we actually want to split up our system into services. Each service has its own database. But then there are things that we need to do that then span multiple databases that become harder. And in particular, it can be challenging to maintain invariants. We can no longer just leverage ACID transactions to do this. And in the next segment, I'm going to look at how you can use an event-driven approach to accomplish this.